Let's take a look at another situation here. This is what if you have a particle that's confined to move on the circle that's shown below? So this is this segment right here. What's the probability of finding it in that particular segment? Okay. Now, in cases like this, it's more convenient to express psi as a function of theta. You can think of theta as the angle that you make with the x-axis. So if you imagine a line from the origin to a point on the circle, the angle that that line makes with the x-axis, x-axis is theta. So we're going to integrate from theta 1 to theta 2, and as you can see, theta 1, let's just say that's about 45 degrees. So that's going to be pi over 4, and theta 2 would be 90 degrees. So that's going to be pi over 2. So what's the probability of finding it in that segment of the section of the circle? What you need to do is integrate psi of theta, which is a function of theta squared, d theta, from theta equals theta 1, 2. Right. So that would be the probability of finding it with that. Now this is if psi squared is given as probability per radian. Okay. By the way, what would happen if you were to integrate this from all right, let's look at the second case. We'll get back to this. I lost my train of thought there. All right. So that's the case. What if it's per unit length? Well, how is length on the circle? So how is length of the arc related to the angle? What's the circumference of a circle? 2 pi r, right? So if the radius here is r, the length, this length right here is just r times delta theta, right? So that's just r times theta 2 minus theta 1. So that means dl, okay? You're going to integrate with respect to length, dl will just be equal to r times d theta. Okay. So the integral would be, in this case, integral of psi squared dl from L equals, okay, let's call this L1 to L2. Okay? L1 to L2. Okay? But if psi is a function of theta, you can express dl in terms of theta, so you would say dl is r d theta. So this is going to be integral of psi squared times r d theta. Okay? So this is what you need if this psi squared is per unit length, okay, multiplied by the length, that will give you a unitless quantity. D theta is radians, doesn't have a unit there. But since you're changing your unit from changing your integration variable from L to theta, you're now going to integrate from theta at L1, which is theta 1, to theta at L2, which is theta 2. So it's psi, even though it's given as a function of theta, happens to be given as probability per unit length, then you have to multiply by r before you integrate over theta. If it's given as per radian, then you don't need to multiply by r. Okay? Now, what would happen if psi is constant? What if psi is constant? Psi squared is constant. Then, over the entire circle, can we calculate what absolute value of psi squared is? Well, then you're going to say the integral from 0 to 2 pi psi squared r d theta must be equal to 1. So what is your psi squared? Absolute value of psi squared times integral of r d theta from 0 to 2 pi must be equal to 1. Okay? So absolute value of psi squared times what's the integral of r d theta? That's just r times integral of d theta is just theta. So r times theta from 0 to 2 pi. So theta evaluated from 0 to 2 pi. So that's just going to be 2 pi minus 0. 2 pi times r is equal to. Note that this is just the circumference. Right? So absolute value of psi squared is just equal to 1 over the circumference, 1 over 2 pi r. It's uniform throughout the circle. Now, this is if psi squared is per unit length. Is per unit length. But if psi squared is per unit radian, then you should be able to show that psi squared is just 1 over 2 pi. Or the absolute value of psi is 1 over square root. Right. So that's constant. All right, let's take a look at this one. If psi is a function of r and theta, you can express instead, sometimes it's more convenient to express psi as a function of polar coordinates rather than Cartesian, especially if you're dealing with a problem that has circular symmetry. So here we're interested in finding the probability of a particle in a circle of radius a. Okay? So in these cases, it would be more convenient to use, instead of x and y, you replace x and y by r and theta. And how do we replace x and y by r and theta? If you recall, if this is your point, x, y, this is going to be your x, this is going to be your y. You can define r as the length of the distance between the point and the origin, and theta is the angle that you make with the x-axis. So you can see that sine theta is opposite over hypotenuse, so y over r. So you can say that y is r sine theta. And cosine theta would just be x over r, adjacent over hypotenuse. So x is just r cosine theta. So how would you write then the probability of finding the particle in a circle of radius a? So you just say integral of psi squared, and so you integrate with respect to theta and r. Do you just say dr d theta? R from 0 to a and theta from 0 to 2 pi. You want the full circle, right? So you go 0 to 2 pi. Go full circle, theta goes from 0 to 2 pi, and r to a, that's 0 to 2. Will that work? Let's look at psi squared d theta dr. Okay, this is first unit. Remember, this is a two-dimensional problem. This should be per square meter, right? Theta is radians, national unit. R is length, so that's meter. So dimensionally, there's something wrong here. That's not quite right. Well, what you need to do is this. Look at the differential element here. You need an area, okay? An area is not, the area, differential unit of area is not equal to d theta times dr. So imagine, okay, let's take a look at the circle here. Two concentric circles right there. Okay, so let's imagine that area right there. That difference right there is delta theta, okay? And and this difference right here is delta r. Okay? Now, as you make delta theta and delta r very small, so you have d theta dr, okay? What would be that area right there? Well, what is this length? If that's delta theta, that length is, remember, is r, okay, r delta theta, right? So if R1 here and R2 are significantly different, then you're going to have to, this length up here and the inner length would be different. But if your dr, if your R2 and R1 are just differ by an infinitesimal amount dr, then you can say that this dl, right, this length right here and this length right here are going to be the same, and they're going to be dl. So you're going to say dl is equal to r d theta. Okay? So length, that length and this length would give you dA. So dA in this particular case would be r d theta, okay, times r. So what we need to do then is we need to integrate psi squared. Okay. First, we integrate it with respect to theta. Okay. Then we multiply the result by r, and then we integrate it with respect to r. 0 to a, and it's going to be from 0 to 2 pi. Or you can just rewrite this. You can just say psi squared d theta, and then r squared dr over here. 0 to a. Now the order of integration doesn't matter, so you can write it this way also. You can say psi squared times r, that should just be r, dr from 0 to a, and then whatever the result is, you integrate it over theta from theta equals 0 to 1. Now, let's verify that this is in fact correct. What would be the integral of just the integral of r dr d theta from r equals 0 to a, and from theta equals 0 to 2 pi. That would be, let's just separate them. So let me put d theta here from 0 to 2 pi, and you have r dr 0 to a. And that should just give you integral of r dr is r squared over 2, evaluated from 0 to a. And then that result, you integrate with respect to theta from theta equals 0 to 2 pi. So what's the integral of r squared over, what's r squared over 2 evaluated from 0 to a? This is just going to be a squared over 2 minus 0 d theta, integral from 0 to 2 pi. So that would be a squared over 2, which I can just factor out, integral of d theta from 0 to 2 pi. And that's just a squared over 2, theta evaluated from 0 to 2 pi. That's just a squared over 2, 2 pi minus 0. That's a squared over 2 times 2 pi, 2 cancels out. That's just pi. That's just the area of a circle of radius a. Does that make sense? Well, if you add up all of those little areas for all possible thetas and all possible r's, from r equals 0 to r equals a, that just gives you the area of the circle. That's pi. Okay? So, this is your integrate element of the area that you need for the integration if you're using polar coordinates.